Hey there, everyone. We are in section 1.3 of the textbook today, and this is called New Functions from Old. Now, this lecture is a little bit longer than the first two because it's got a lot of important content all jammed together, but this is, I think, a little bit easier than some of the other material. So there's a lot of it, but I think a lot of this you'll remember from pre-calculus. The first major part of this section is talking about how to take a function f and do certain transformations to it and see what's left over. This is an idea that we're going to deal with a lot when we start talking about derivatives in calculus. We'll see four different examples. The first is taking f of x and adding or subtracting some constant outside. The second is taking f of x and adding or subtracting some constant inside the function. The third is multiplying a function outside. And the fourth is multiplying inside. All four of these do slightly different things to a function, but when you combine the power of these four, you can do a lot. I'm going to show you what all four of these do, and I'm going to use this example function for the next bunch of slides. This is the function x cubed minus 3x. So this function says you take as input some number x, you cube it, you multiply it by 3, and then you subtract those, and whatever you get, that's your output. Now, if you were to graph this function, like if you were to go on Wolfram Alpha or use a graphing calculator or something, it would look kind of like this. As you go to the left, it goes down to negative infinity, but then it goes up above the x-axis for a little bit, it turns around, it comes back down, then it does another U-turn and goes back up to infinity. All right, moving on. The first transformation is adding or subtracting a number on the outside. So first I'll tell you what this does. Then I'll explain why it does it, and then we'll see a nice graph on our graphing calculator. First off, adding a positive number c, so if c is positive, that shifts your whole graph vertically up by c units. So you've got this picture, and if you add 1, it takes the whole picture and moves it up 1 unit. If you add a negative c, or phrasing that a different way, if you subtract a positive c, that moves you vertically down. So if you subtract by 1, that takes everything and moves it down by 1. Now, why is this? One of the points on this graph of f of x is 2, 2. So let me show you 2, 2. And that's because when I plug in 2, I get 2 cubed, that's 8. Minus 3 times 2 is 6. So 8 minus 6 is 2. So that's one of the points there. Now let's define a new function g that we get by transforming f by adding 3. So we're doing this with a plus 3. So now the point 2, 2 on f becomes which point on g? Well, if I plug in 2, g of 2 is now f of 2 plus 3, because that's just our formula right here. F of 2 is 2, so that's 2 plus 3 equals 5. So this is showing us the idea of why everything moves up by 3 when I add 3 on the outside. It's because I have whatever height I had before, and then I go up 3 more. And that should make sense that if you subtract a number, the same thing happens in reverse. If I define h of x to be f of x minus 7, then what happens to the point that was at 2, 2? Now the point at x equals 2 is f of 2 minus 7. F of 2 is 2, so that's 2 minus 7 equals negative 5. So every point that was on f, I evaluate it, that's the height it was before, and then I subtract 7, and that's the height it is now. So every point moves down by 7. Now let me go into our graphing calculator, and I'm going to show you a nice little example for each of these transformations. So the first function I have graphed in red, and you can't see it here because the blue one is directly on top of it, is our x cubed minus 3x. In blue is what happens when I add c, and I have a little slider here for c. So when c is 0, they're obviously exactly the same. That's why you can't see the red one. When I make c positive, the blue one now slides up. When I make c negative, it slides down. So this should make some kind of sense. When you are, say, subtracting 4 from f of x, every point moves down exactly 4. If you take any point on the red and you move down by 4, you get a point on the blue. And so that's all this does. It's a vertical shift up and down. Positive c means up, negative c means down. Okay, so that's probably the easiest one of the four. Next up is, well, this looks almost the same, but the difference here is that instead of adding a c on the outside of the function, that's like adding or subtracting it to the y value, here we're adding or subtracting it to the x value inside. Now what I'm going to say sounds a little bit backwards, but it's actually correct. If I add a positive number c inside, it shifts it to the left by c units. So we have some kind of natural inclination that adding a positive number means either going up or going to the right. But here we get a little bit of a reverse effect. Adding c moves it to the left. If I subtract a positive number or add a negative number, that shifts it to the right. Now this is a little bit weird, but I want you to understand why that's the case instead of just memorizing this fact. Let's think about what happens if I take f of x, the same one from before, and I add 5 inside. So I'm going to define this new function g of x is f of x plus 5. Now my claim is that because we're adding 5, this new graph g will look the same as f originally, but shifted to the left by 5 units. So let's see why. What is the value of g at x equals 0? So I'm asking, if I look at an x value of 0, right, on the axis, what height do I get? That height is going to come from some point in f. Is it the point from 5 to the right or 5 to the left or whatever? Well, g0, just by our formula right here, g0 is f of 0 plus 5, which is f5. So think about that for a minute. G gets its value at 0 from f's value 5 to the right. So you should think about g as pulling its values from 5 to the right over to where it is. The value of f at 10 looks 5 to the right at 15 and then pulls it over. So that means g is to the left of f. So how do I get from f to g? I shift to the left by 5. Okay, let me say that one more time. The values at g, like g of 0, come from 5 to its right. So that means if I take any point on f, for example at 5, what happens when we plug in 5 here? Okay, this is a little bit of a big number. 5 cubed is 125. 3 times 5 is 15. So that's 110, I think. So a point on f is 5, 110. The point that I get on g is 0 because g pulls its values from 5 to the right. 0, 110. And that's exactly what this tells us. G of 0 is f of 5. So the height of g at 0 is the height of f at 5. So we go 5 to the left. So the plus tells you how far away you're pulling it from. Let's look at our graph again. Starting with the exact same function, and again we have the red one underneath the blue one so you can't see it, but if I make c positive, the blue one's the new one. As I make c positive, it goes to the left. As I make c negative, it goes to the right. So for example, f of c minus 5 has taken f in red and moved it 5 to the right. Now why is that? Because in this graph, what is the height of the blue one at 5? Well, it pulls its height from 5 to the left. It pulls its height from the red one at 5. Okay, so to summarize, adding or subtracting a number inside the function causes what we call a horizontal shift left or right. And it's got kind of the backwards fact that a positive number shifts it to the left and a negative number shifts it to the right. That's our second out of the 4 transformations. On to number 3 now. The third one takes our function and multiplies, not adds, but multiplies a number, positive or negative or 0, in front. Okay, now I wrote out a bunch of cases here. Don't let that scare you. I kind of wrote them all out in a ton of detail. the key is that multiplying by a number causes a vertical, so adding outside was a vertical shift. Multiplying outside is still a vertical thing, but it's a stretch or a shrink. When we say stretch, we mean that the function has been elongated. When we say shrink, we mean that it's going to be kind of squished together closer to the x-axis. So depending on whether c is positive or negative, bigger than 1, less than 1, you have a different combination of these. If c is greater than 1, we have a vertical stretch. So for example, if I take f and I multiply it by 2, my function gets stretched vertically. If c is exactly 1, well, it's obvious then that nothing changes, because 1 times f of x is just f of x, nothing changes. If c is positive, but between 0 and 1, now my function gets kind of squished down a little bit closer to the axis. So if it's like 1/2, then all the heights become smaller. If c is actually 0, well, now you're multiplying by 0, so your function just becomes the straight line 0. And then we've got these 3 cases where it's negative, and these correspond almost exactly to these same 3 cases where it's positive, except in addition to whatever you do, you also have a vertical flip. All of the negative ones become positive, and all the positive ones become negative. So if you're between -1 and 0, you still have a shrink, just like between 0 and 1, you have a shrink, and you have a flip. If it's exactly -1, if it was +1, nothing happened. If it's -1, there's no stretch or shrink, but you still have a flip. And lastly, if it's less than -1, like -5, you have a big stretch, and then you have a flip. Okay, so even though this looks like a very complicated thing, you've got just the one idea that you're stretching or shrinking, and maybe you're flipping, and just all the different combinations of those. Now, I do have a graph showing what happens here. Let me first explain, again, why. This one I think is pretty obvious, maybe at least more obvious than the last one. Suppose that I've got my function f, same one as before, and I define this new function g as 5 times f. Then we ask the same question as before, which is that if I start with 2 on f, what does that correspond to on g? What happens to the point at x value 2? Well, now g of 2 equals, by our definition here, 5 times f of 2, which is 5 times 2, because f of 2 is 2, which is 10. So at x value 2, my height went from 2 to 5 times 2. So all my heights get 5 times bigger. 2 goes to 10. If I had a point at height 10, it would go to 50. If I had a point at height 0.1, it would go to 0.5. All the heights get 5 times bigger. And that applies to negative side too. If 2 goes to 10, that means -2 goes to -10. It gets stretched the other way. On the other hand, this is a different example. What happens if I multiply by -1/2? Same kind of idea. That 2 in f becomes h of 2, which is by our definition -1/2 times f of 2, which is -1/2 times 2. And the 1/2 and the 2 cancel, leave me with -1. So that point at height 2 at the same x value now becomes -1. And why is that? It's because the 1/2 meant all my points shrunk by a factor of 2. So height 2 became height 1. And then my negative sign said now flip them. So it's a shrink followed by a flip. Let's look at our graph of the same function. Now here, the starting point where they overlap is a 1, right? Because 1 times f of x is the one that doesn't change it. Let's make it positive. Okay, so if I make c 4, for example, then all of my points get stretched by a factor of 4. This one here gets stretched 4 higher up to there. This one down here at -2 gets stretched 4 times lower down to -8, and so on. The point at height 0, when you stretch 0, you stay at 0, so that one doesn't change. So large values of c stretch me vertically. Notice that whenever it's 0, it stays 0. Because you can't, if you multiply 0 by anything, it stays 0. So those never change, but everything in between gets stretched. Now if I bring c down in between 0 and 1, let me zoom in a little bit here. Remember, red is our original function. If I bring c down, here's 0.4. Okay, so now my point at height 2 became a point at height 0.8, and that's because 2 times 0.4 is 0.08. If I bring it negative and between, negative and between 0 and 1, this is a shrink and then a flip. And if I make it more negative than 1, now we have you can think about this two ways. You could think either a flip and then a stretch, or you could think about it first a stretch and then a flip. Those end up in the same thing. Okay, so a few different cases, but I hope the graph makes it kind of obvious what's going on here. We're on to our last one of the 4. And this is when you multiply by a c inside. Now, just like in the second example, where adding a c inside did kind of a backward thing, adding moved you to the left, and subtracting moved you to the right. This, again, is an inside thing, and so it's going to seem backwards. But it will have the same kind of logic as before. If I multiply by something greater than 1, because it's happening inside things do horizontal things. Just like, let me remind you, f of x plus c, that was a horizontal shift. So things inside the function do horizontal things. But it's a shrink or a stretch. So our graph is either going to get stretched out wide or shrunken to be more narrow. And if c is greater than 1, that shrinks it. If c is between 0 and 1 but positive, that stretches. If it's between negative 1 and 0, it stretches and flips. And if it's less than negative 1, it shrinks and flips. For the same kind of backward reason as before. And we'll use an example again. Let's suppose that we define the function g to be f of 5x. That means that g is grabbing its x values from the values further away. So for example, f of 2 has the point 2, as we've seen over and over again. But g of 2, where does g of 2 come from? G of 2 gets its point from 10 away. So if I want to figure out what happens at 2, it does the same thing that f did way further away. So whatever happens to f, it's happening to g in a much narrower time range. G is hitting the same values, but faster, 5 times faster. So here, g of 2 is f of 10, which is, let's see, this is going to be a big one. 10 cubed, that's 1,000, minus 3 times 10 is 30. So 1,000 minus 30 is 970. So f, when does f hit this big point? It takes all the way till 10. When does g hit it? G hits it much faster, so g only hits it at 2. So the points that were further away from f get brought in very narrow to g. So multiplying by this 5, a number bigger than 1, shrinks it in because it all happens a lot faster. And same kind of idea in reverse. If this were a 1/5, the values of f happen slower in g, so they get pulled out further apart. And once again, we have a nice little graph. I'm not going to write this one out, but it's the same kind of idea. If you have a 1/2, that means the things that happen in h happen it takes twice as long for them to happen. The value of h at 2 is the value of f at 1. So the values get spread apart further. That's a stretch. So hopping into our graph, one last time that we'll see this, well, I think there is actually another one, but the last time we'll be seeing this with one transformation. If I move c to the right, if I move my slider to the right, that's like c of 5x. Let's see if I can hit 5. Then all my points happen very, very narrowly. So this point here on f crosses the x-axis at 1.732. But on g, it happens much faster. It happens at 0.1732. It happens 10 times faster. If I move my slider to be between 0 and 1, now my new function is much more spread out. So I've got the red one is f, and the blue one happens much more slowly. A negative is the same thing, but a horizontal flip. And a big negative number is, again, the same as a big positive number, but a horizontal flip. So bigger than 1 shrinks. Between 0 and 1 stretches. And then when you add a negative sign, that's a horizontal flip. So here's a quick recap and one graph where you can see all of these in action. Adding or subtracting a number on the outside is a vertical shift. Adding or subtracting on the inside is a horizontal shift with this backward effect. Multiplying on the outside is a vertical stretch or shrink, and maybe a flip if you have a negative. Multiplying on the inside is a horizontal stretch or shrink, and maybe a flip if it's negative. And again, because it's inside, just like the other inside one, it has that little bit of a backward seeming effect. And these can be combined too. You can make any of these transformations all at once. So here I've defined this second function to be our original f in red, but with a slider for each one of these things. We can slide all 4 of these different variables. This is the vertical shift up and down. The vertical stretch. B is the inside multiplier, so that's a horizontal stretch or shrink. C is the inside adding, so that's a horizontal shift. And D is the vertical shift. Okay, so this is not very useful when you see all of them moving together, but if you want, you can pause any 3 of them and see what the other one does. So then that's clear that that's a vertical shift. You could pause this one. You could start up the F again. See, that's clearly a stretch horizontally or a shrink horizontally, and maybe a flip, and so on. Now, just a reminder that all of the demonstrations I use from Desmos, I put in links on our course calendar on our course website. So you can go and you can see any of these. You can interact, you can play, change around with the sliders, try to make sure that you understand the concepts. Okay, that was the first major part of 1.3's material, these transformations that take you from some functions to other functions. There's also a couple other topics in this section that we need to cover. The first is composition of functions. This is kind of another way of getting new functions, but in this one we take 2 old functions and we stick them together, we join them together to get a new one. This act of composition or composing just means do one first and then the other. So you're like chaining them together. So for example, let's think about the function f of x equals x squared. You could think about that as a verb. What does that function do? It squares. You can also think about the function g of x equals x minus 2. What's the verb for that function? What does it do? It subtracts 2. So these are 2 different operations. Now, how do we combine them? So first, take a look at this notation here. This is the composition notation. It looks complicated, but there's just an order of our operations here. This says do g of x first. That gives you some result, and then do f of that. So first apply g because it's the innermost, and then apply f to the result. Now, I think that the diagrams that I do where you have these boxes, you have a box for your function, and you've got your input and your output, I think that's a great way to picture composition. In this case, g is the innermost one. So what this says is you have some input x, you feed it into your g box, some output comes out of it, you take that output and you feed it directly in as the input to f, and you get some output to that. So you're taking these 2 functions, these 2 boxes, and you're literally joining them together. Now, what does it do for these actual functions? Well, f is the squaring function, and g is the subtracting 2 function. So this says first subtract 2, then square. So in terms of our picture, first subtract 2, so x becomes x minus 2, and then square. Now you're not squaring the x, you're squaring the input, and here the input was x minus 2, so this is x minus 2 all squared. The way you would think about this symbolically is first you have g of x. Whenever you see a g of x, you just replace it with what it is. So the g of x inside becomes x minus 2. Now, how do we evaluate f of x minus 2? That just means, whenever you see something like f of x equals x squared, that means take whatever's inside and plug it in wherever you see an x on the other side. So we have an x minus 2. So we take an x minus 2 and we turn the x into x minus 2, and that means we get x minus 2 squared. So let me repeat that. That's important. When you see a function, what you're really doing is saying whatever your input is, turn all of the x's into that on the other side. So you plug in x minus 2, that means your result is x minus 2 squared. So first we do the inside, then we do the outside, and that's what we get. Now what you might notice is that the order here is important. What if instead I composed them in the other order? This says do f first and then do g. So in terms of our boxes, we take our input x, we feed it through the f function box and get some output. Then we take that output and feed it in directly as the input to the g box, and we get the output there. So first we're squaring, lost my parentheses there. First we're squaring, that's what f does, and then we're subtracting 2 because it's on the outside. So first we do f of x, that's x squared, and then we apply the function g to x squared. G says take whatever you give me, and I'll give you back that minus 2. So if we give g x squared, it gives us back x squared minus 2. G is the function that takes whatever you give it and subtracts 2. So the first composition here gave us x minus 2 all squared. This one gives us x squared minus 2. And these are different. This is really important. These are two different numbers. For example, if I do, let's say x equals 3. Then this is 3 minus 2 squared. That's 1 squared is 1. But this is 3 squared minus 2. That's 9 minus 2. That's 7. So the order matters. The order of a composition makes a big difference. And that order, our order of operations, is always inside to outside. Okay, so that was a quick one-slide topic. The next one is odd and even functions. This is a quick definition of an even function and an odd function, and then a quick test to help you tell if a function is odd or even. We call a function even if it's symmetric over the y-axis. So this one's the y-axis here. That means if I can take the y-axis and I flip it, okay, that looked a little silly. It looked like I was just drawing the function in. What I really mean is mirror the function over this line. If I get the same thing that I started with, then it's an even function. So you can imagine this parabola, if I flip it, I can't really do that with my arms, then I get the same function I started with. What that means, for example, is that the point 2, 4, when I flip it, that means I'm now looking at it with an x value of negative 2 instead of positive 2. It needs to have the same height, also 4, because it's even. So the heights have to be the same when I flip. So if you have the graph of a function, it's easy to tell if it's even just by looking at it. But sometimes, as we'll see in an example, you don't have a graph, you have just some formula. Like maybe you have f of x equals x squared. And so we need a nice test. And here's a really easy way to see it. A function f of x is even if, when I plug in negative x, I get the same function I started with. So let me write that out in words. It's nice to see written out. If I plug negative x into f, I get what I started with. Okay, I'm going to not quite have room to write this. I get what I started with. Okay, we'll see an example of this in a minute, but the idea here is this is like saying, for example, in this picture, f of negative 2 has to equal f of 2. So think about this really as explaining why this test works. Being symmetric over this line means that my point over here at 2, if I look at negative 2, I have to have the same height. If I had a different height, I wouldn't be symmetric. So f of negative 2 has to be 2, has to be f of 2. F of negative 10 has to be f of 10. And that's exactly what this is saying for all x. So that's even. A function is odd if it has a different type of symmetry. A function is odd if it has rotational symmetry, 180 degrees, around the origin 0, 0. So here's the graph of x cubed. If I take this whole function and I rotate it 180 degrees around the origin, so I rotate it 180 degrees, I get what I started with. So this point 2, 8, that's on the graph because 2 cubed is 8. If I rotate it 100 degrees, that's like making both the x and the y coordinate negative. So that becomes -2, -8 right here, and that point is on the graph. So this graph is odd. If I looked at -2 and it wasn't -8, if it was like -10 or something, I wouldn't have that rotational symmetry. My point would be in the wrong spot. So here, my test is very similar. It says if I plug in a negative x value, then what I need to get back is not exactly what I started with, it's negative what I started with. So if I plug in -2, I shouldn't expect to also get 8. I should expect to get -8. So if I plug in a negative x, I get back negative of what I started with. Just to write that out explicitly, f of -2, so what value should I get? Well, if it was even, we would have said f of 2, but for odd, we add that negative sign, so it's negative f of 2. So that means what I get at -2 should be -8, and that's what we have here. Now, a function can be odd or even or neither. So if you're asked whether a function is odd or even, there are plenty of functions that are neither odd nor even, right? If you think about most functions are not going to be lucky enough to have one of these types of symmetries. So let's go through a couple of these quick examples and determine if they are odd, even, or neither. Now, the best way to do this, we've got our two tests. The test for even is that f of -x equals f of x. So that says when I plug in -x, I need to get back the same thing I started with. The test for odd is f of -x equals -f of x. So the way that we're going to test these is we're going to plug in -x, and we're going to see if what we get is f of x, then we're even, negative f of x, in which case we're odd, or neither, in which case we're neither. So this is actually pretty quick to do. So let's start here, f of -x. Now you want to be careful how you plug in a -x. The way you plug in something is you literally say, everywhere that I had an x, replace it with what I'm plugging in, a -x. So it would be wrong, this is the wrong answer, to say -x to the fourth, because that implies that your order of operations is you take x to the fourth and then you multiply by -1. But that's not right. This is -x to the fourth. That negative is the most tightly grouped part of the order of operations because it's what we're plugging in. Now you might remember from pre-calculus that if you take a negative and you raise it to an even power, it cancels. That's because if you were to write this out all the way, this would be -x times itself 4 times. And if you have an even number of negative signs, that becomes a positive sign. Okay, so look what we've written here. We plugged in -x, and what we got back was x to the fourth. X to the fourth is what we started with. So we did some arithmetic in the middle, but what we found is that f of -x equals f of x. That means this one is even. Okay, moving on. Let's do g of -x. Again, we have to make sure that our grouping is correct. This is -x in parentheses cubed minus 3 times -x. So what happens when you have 3 negative signs? Negative times negative times negative is negative. So we get -x cubed plus 3x. And our question is this the same as what we started with? If so, it would be even. Well, no, it's not the same. But is it negative of what we started with? It kind of looks like it is. So let's try to pull out a negative sign. negative, and then what's left? An x cubed minus 3x. And hey, that's exactly what we started with. So this is negative g of x. So g of negative x equals negative g of x. That's the test for odd. So this is an odd function. Okay, maybe this would be a good place to pause for a second. Try these next two on your own. I'm going to go ahead and do them now. Maybe you paused, maybe you didn't, but let's see if we can work through them. Let's plug in h of negative x. Now again, the negative has to get grouped very tightly with the x. So this is e to the negative x squared. Negative x squared, well, that's two negatives multiplied together. That's a positive. So that becomes e to the x squared. But that's exactly what we started with. That's h of x again. So this one's even. Last one. We plug in negative x. That's negative x all squared plus negative x. Simplifying this a little bit, the negative x squared just becomes x squared minus x. Now, is this what we started with? No, because we have a plus and a minus, so it's not even. Is it the negative of what we started with? Also no, because the negative of this would be negative x squared minus x, and this is a positive x squared minus x. So it's not what we started with, and it's not the perfect negative of what we started with. That means it's neither. Okay, so we saw some examples here of where your function could be even, odd, or neither. Now, one thing I didn't address, is it possible to be both? Is it possible to be both even and odd? I'm not going to, well, I'll tell you the answer. The answer is yes, it is positive, but only in a very, very, very particular case. So I'm going to leave you to think about this. This is a kind of a good conceptual test. Can you think of a function that is both even and odd? There's only one of them that I can think of, and it's a pretty familiar, easy function. So I'll let you think about that. Okay, so this has already been a long lecture. We still have a little bit more to cover because this is just a very long section in the textbook, and especially these sections in Chapter 1 tend to be long because there are a lot of review topics, but the lectures will shorten out, I hope, as we get into future chapters. I think this is the last topic. The topic of inverse functions. This is definitely something you probably learned about in pre-calc and maybe even in algebra before that. If we have a function f of x, then the inverse function, which we write like this with a little -1 superscript, that's just pronounced f inverse of x. This is the function that swaps the x and y values of the original function. So if you had a point 1, 3 in f, that's an x value of 1 and a y value of 3, f inverse is going to have a point where they're swapped. It's going to have an x value of 3 and a y value of 1. So you take all the points on f and you swap them, and those are your points of f inverse. Now, one thing I want to point out is this -1 notation I've never really liked because we also use a -1 superscript as like a reciprocal. Like, for example, sometimes we write 5 to the -1 equals 1/5. This does not mean that here. It does not mean reciprocal. It's not 1 over f of x. It's kind of just, unfortunately, a different use of the same symbol. So when I talk about swapping x and y, another way you can think about that is symmetry over the line y equals x. So y equals x. That's the line with slope 1 and y-intercept 0. Let's try to draw that line. Let's see if we can place this a little better there. Okay, so that's the line y equals x. When we talk about swapping y equals x, that's like we're taking that diagonal line and we're flipping things over it. So if you think about that point I just said before, if you had a x value of 1 and a y value of 3, you got this point here, you flip it over the line, and now you have an x value of 3 and a y value of 1. So your point kind of got flipped over this line here. What would happen to this function? This is, for example, y equals x squared. If we try to flip it over the line, we're going to see that we kind of have a problem. this right-hand side, if I flip it over this line, looks like this. Not exactly to scale, but close enough. This left-hand side, if I flip it over the line, looks kind of like this. So if I try to talk about the inverse of the green function, then what I get is this thing. But this is not even a function. Remember, one of the key facts is one of the key things that makes a function is that for an x value, there's only one y value. But this has a problem because, for example, if I look at x equals, let's say x equals 5, at x equals 5, let's make this a straight line here. At x equals 5, we have 2 y values, and that's a problem. So what this tells us is that the inverse of a function doesn't always exist. This x squared function does not have an inverse because when we try to flip it, the result is not really a function, so we have to be more careful. There's a test that tells us if a function is going to have an inverse, and it's called the horizontal line test. You may have heard about this before, and you may have heard about something called the vertical line test. The vertical line test tells you if a curve is a function at all. Nothing about the inverse, just if it's a function. The horizontal line test tells you if the inverse is a function. So we say that the horizontal line test, a function passes the horizontal line test if it's impossible to draw a horizontal line that passes through the function more than once. If I can draw a horizontal line that passes through the function more than once, like I did there, then it can't have an inverse. Now, why is that? That's because if I flip this over the curve, this horizontal line becomes a vertical line that passes through the inverse twice, and that means it's not a function because it would have 2 different y values. So this fails the horizontal line test. I'll agree with the HLT, horizontal line test. So this does not have an inverse. However, this is a kind of tricky thing. If I cut it in half and only allow half of the function, you see now I'm doing that thing where I state the function and explicitly state the domain instead of letting it be implicit. This does pass the horizontal line test because I've cut the function in half. Everywhere I draw a horizontal line crosses the function once or 0 times, but never more than once. So this has an inverse. Now, what is the inverse? Well, let's imagine that we have the line y equals x. Let's imagine flipping. It looks like this. This is the function f inverse of x equals the square root of x. Now, when you think about the inverse of a function, we've been talking about it in terms of symmetry, but you should also think about it as the function that reverses the original one. So in our normal picture where we have something like the f box, which sends x to f of x, you should also think about the f inverse box as going backwards. So if I have the f inverse box, that takes f of x and turns it back into x. It reverses the process. In fact, just think about taking that whole box and reversing it. Draw an f on the box, but draw it backwards. That's what the inverse does. This does some combination of things to give you your output. This really is just the box that reverses the process. That makes sense here. Squaring something and taking the square root reverse the process. If I take 3 and I square it and get 9, this takes the square root of 9 and gives it 3 again. So inverting a function reverses the process. But I also could have restricted it to the other half, and that still passes the horizontal line test. This is the version where x is less than 0. If we draw our y equals x line again, and then reflect it. This one might take a little bit of thought, but this one looks like this. This turns out to be negative square root of x. Now, you might remember from arithmetic and algebra or pre-calculus that when you're taking the square root of both sides, if you're trying to like solve for an equation, usually you see something like a plus or a minus square root of x kind of thing. That plus or minus is really saying we don't know which side of the squared function we might have come from. If you're squaring something and get 9, that could have been because you squared plus 3 and got 9, or minus 3 and got 9. So that square root is not really a function, and that means you have to say plus or minus separately because there are two possibilities and you don't know which. But when you've restricted the function to either one side, then you know it must be the plus square root of x, like on the last slide. Or if you've restricted to the minus side, it must be the minus square root of x. That's here. Now, how do you calculate the inverse of a function? Well, if a comma b is a point on the graph of f of x, then the whole point of the inverse is that means that if I swap the x and y values, then b comma a must be a point on f of f inverse. Sorry, on the graph of f inverse. That's a mouthful. So what this tells me is that if I want to find a formula for f inverse of x, what I can do is swap the variables and try to solve. And really, I shouldn't say swap the variables. That's a little bit confusing. What I should really say is solve for the independent variable. So let me put that. That's a better way to put it. Solve for the independent variable. So the book has an example that we'll do now. They explain all of the details about this. I won't go into details. I think it's the first one of the section maybe. It tells you that the speed at which a cricket chirps is related to the temperature outside, which I think is a pretty interesting fact. And it's roughly, on average, this function. So T in this one is a temperature. And this is I think the chirps per minute of a cricket. So you should think about this as our box. The function is called C. If I put in a temperature, then the box does its thing. In this case, what it does is it multiplies by 4 and then does minus 160. And what it spits out is the number of chirps. So my function is a little machine that takes in the temperature and spits out the chirps. We want the inverse, where if I put in the chirps, it does whatever, and it gives me back the temperature. So if I say they're chirping at 100 chirps per minute, this function is going to tell me then what the temperature must be. It's reversing that process. So the way that we're going to solve this, we're going to write this c of t. The of t here is a little bit superfluous. So let's just write this as c equals 4t minus 160. We want to solve for the independent variable. In the original function, c depends on t. We want to reverse it so that t depends on c. That means we want to isolate t. So the way we isolate is that we move everything else around it somewhere else. So we take that plus 60 and we move it to the other side. Well, it's a minus 160, so it gets plus 160. And then we take that 4 and we divide it. And we get t equals, you could write it as c plus 160 over 4, or you could simplify it to c over 4 plus 160 over 4, which is 40. So I said before, if I had 100 chirps per minute, what is the temperature? If all you had was this, you might have to plug in some numbers and try to guess it. But now that you've got the inverse, that's the machine that reverses it for you. So my temperature, if I have 100 chirps per minute, is 100 over 4, that's 25, plus 40 is 65. And I forget if this is Celsius or Fahrenheit in the book, but whichever it is, that's the temperature at which crickets chirp 100 times per minute. So it's really nice to think about the box pictures here. The inverse is the machine that reverses what the original function does. Okay, so sorry that this was a 50-minute lecture. We're still going to have the video where we do 5 exercises. I do hope that on average these will be about 50 minutes with the lectures and the exercises together, but at the beginning they are going to be a little bit long. As always, if you have any questions, definitely come to office hours, let me know. You could ask at the Calculus Help Desk, or you can email me. I hope this has been helpful.